Let's design the slab for our simulated little project. Here is the floor plan that we had settled on, and here are the loads. And if you go back to the loads videos, we ended up deciding on 65 PSF live in the offices, 50 PSF office plus 15 PSF partitions. And we had some choices for the corridor, and one of them, which I will use, was 100 PSF live in the corridor. And we won't do the roof, but the roof live was 20 PSF. The dead load for the floor, was 16 PSF, and the dead load for the roof dead was 8 PSF. Let's design the slab in this little section here with the 100 PSF live, 16 PSF dead, plus the self-weight. So let's summarize that. Corridor slab. (100 PSF live), 16 PSF dead, and self-weight dead, which we don't know yet. Let's determine the thicknesses. And what we have here are the slab spans going like that. And what I'll try to do is to redraw that from the section view. So we've got 1, 2, 3, 4, 5 beams. I'll draw the first 5 beams and the slab going over it. It won't be exactly to scale, but roughly that spans about 10 feet, 8 feet, 9 feet, and 9 feet. Okay, so let me try and sketch that out. Let me get some grid on here. Okay, so what did I say? 10, 8, 9, and 9, roughly. I'll put the real dimensions in a little bit. Okay, so let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 feet, 8, 9, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Oh, we just make it. Okay. So we want, I'm just going to mark these off now. Switch to black. Okay. All the way there. If you look at how I sketched this out, very unfortunately, this dimension goes to the outside of the column, but these 3 dimensions are center to center. So I'm going to try and draw that. Oh, I know what I'll do. I'll just copy and paste. There we go, roughly there. Oh, roughly there. And oops, roughly Oh, something like that. Okay. And something like that. And let me put the dimensions in. Okay, that first span from the outside to the midspan was 9 feet. This is 9 feet 8 inches. Center to center are all the rest of them 7, 10, and 8, 9. 7, 10, and 8, 9. Okay. We need the clear spans to use the ACI moments, and we don't know the width of the beams because we haven't designed them yet. And so looking at this, I'm going to guess that this north-south beam that's 23 feet long, right there, that beam right there, I'm going to guess a depth of 1/12 of that, so 23, let's say 24 inches, and a width of half of that, so 12 inches. So I'm guessing that that north-south orange highlighted 23-foot beam is 12 inches wide. Okay, so I'm guessing, we don't know this for sure, that these are all 12 inches wide. After we design the beams, we'll have to revisit this. And so what we need now are these clear distances between the faces of these beams, because the ACI moments are based on face-to-face clear distances. So we need these. Okay. And so these 3 on the right are easy. You're going to subtract 6 inches off and 6 inches off. So you subtract a foot. So that's 6 feet 10 inches, 7 feet 9 inches, 7 feet 9 inches. This one on the left, from the 9 foot 8, we have to subtract 12 inches on the left and 6 inches on the right. So 1 foot 6 inches we're subtracting. So that makes this 8 feet 2 inches. There you go. Those are LN. And we are now ready to use the ACI approximate moments. I want to clean this up, delete my little construction lines. And there we go. Let me go find those approximate ACI moments and come back. I've got all that sort of stuff. I've got a little thing in here. Where is it? Design aids. There they are. And so the one we have, our slab distances were less than 10 feet. And so if you're less than 10 feet, you can use these equations or these approximations. So I'll copy that. Go back to our slab example. Let's see, where's that? Slab example, no. Where did I put that? Oh, here. Is that where it is? No? Oh, it's in the project. Oh, sorry about this. So, oh, there it is. Design project, slab. There we go. Sorry. Okay, so let me paste in, hopefully. Yep, there we go. Here are the approximate moments we're going to use. And you can see it's WL squared over 12 and WL squared over 14. We need W. We have the LN. So the next thing we need to do is get the thickness of the slab so we can get the W. Now, let's look at this again. And let me delete these. These aren't the real dimensions. Okay, on these exterior spans, the minimum slab thickness recommended is L over 24, and these are L over 28 for all of these. So I'm gonna calculate L over 24 for 9 foot 8 inches. It can be a little less. You could use a clearer, but I'm just gonna use this. 9 foot 8 inches divided by 24 is 4.8 inches. Minimum thickness. Obviously, these are going to be less, the shorter spans and bigger denominators, but I'll do it just in case, just to show you. 7 feet, 10 inches divided by 28, 3.4 inches. And 8 feet, 9 inches divided by 28 is 3 3/4 inches. This is the biggest. I will say 5-inch slab. Okay. So our 5-inch slab has a self-weight 5 over 12 feet times 150 pounds per cubic foot is 62.5 psf. Q ultimate is 1.2 dead, which is 16 plus 62.5 plus 1.6 live, which is 100. Let me do that. I get 254.2 psf. For a unit width, the tributary width of 1 foot, 0.254 kips per foot that we're going to use for the moment calculation. So 0.254. Okay. And WU equals 0.254 kips per foot. You would have to do this for all 4 spans. I'm going to just do this for this first span here, and you can do the rest. So let me get the clear distance is 8 foot 2 inches. So that is 8.17 feet. WU is 0.2454 kips per foot. Let me calculate the moments. WL squared over 12, okay? Which, if you've taken a structural analysis class, is the fixed end moment. Okay, 0.254 times. Oh, I did something wrong. Okay, 8.17 squared 0.254 is W divided by 12. There we go. So this moment here is 1.412 foot kips, and the other moment is 1.21. Okay. Okay. Okay, so we have the moments. I'm gonna do the biggest one and pick the steel out, and we'll go from there. So MU is 1.412 foot kips. MN required is just MU over phi. And I'm gonna switch it to inch kips. So I'm gonna do, I'm gonna type that in, 1.412 divided by 0.9 times 12 is 18.8 inch kips. RN is MN over BD squared. B is 12. Remember, we're doing a 12-inch segment of the beam, of the slab, sorry. And D is H minus 1, and we picked H as 5, so D is 4. Okay, 12 divide, 16 divide, 0.0980 KSI. And I have set in my calculator the equation for Rn to solve for rho, and I posted a video about that. And so it's so handy for situations like this. So I'm just going to solve that for rho. Okay, and what I get is it's very small. Rho equals 0.001658, and AS per foot is rho times BD, rho times 12 times 4. Okay, so that's 48. And it's 0.08 80 inches squared per foot. We need to check AS min. I have a hunch that AS min is going to be greater than that. AS min, it's always 0.0018 for grade 60 times B times H, not D. 0.0018 times 12 times 5. The H was 5. So 0.0018 times 60, 0.108 inches squared per foot. So this controls. And on top of that, it was the biggest moment anywhere because that was the biggest clear span. And it is also the largest load. This was for that 100 PSF load. So this means everywhere in our little building, we're gonna have minimum steel. So we need to go to the chart to find 0.108 square inches per foot. But I just happen to know that a number, I've got this memorized sadly, a number 3 bar is 0.11 square inches. And in this case, we will put 1 bar every foot. So a number 3 every foot. That will give 0.11 square inches squared, 0.11 inches squared per foot. And we're done. Oh, well, you need to make sure that that spacing is less than 18 inches. Of course it is. 12 is less than 18. And also less than 3 times the slab thickness, which is 5. 12 is less than 15, so that's good. And what we're going to have is all the steel in the slab is number 3 at 12 inches on center, positive moment, negative moment. That also, this minimum steel is also the temperature steel. So basically everywhere number 3 at 12 inches on center. And so if you wanted to, you could bend the bars up to the negative regions if you saw the previous example I posted in the flexure section. So there you go. That's the solution for our slab design for our project. What happened was I didn't think hard enough about this. These span lengths are not long enough. The beams could be spread farther apart, I think. Anyway, there you go. Number 3's at 12 inches on center. Yeah, and you know, that will always be the case for grade 60. That minimum steel for grade 60 is a number 3 every foot. There we go. That's it for the slab design for the project.